So as we move on to lesson 1.9, we've talked about working with similar figures and being able to find those missing dimensions. And what else did we, what were the other objectives that we also did? Did you guys finish your notes yesterday after you got, was it this class we weren't able to finish that last, or were we able to do it? Okay, I had class that we couldn't. So indirect measurement, remember we could set up a similar figures situation, and we could use indirect measurement to find the measurement of like a 44-foot building without going out and actually measuring it. Okay, well now we're going to say, what's going to happen if I do apply a scale factor, create a similar figure or a similar object, and then what's going to happen to its perimeter area or maybe its volume if it's a three-dimensional. So if every dimension of rectangle A has been multiplied by 2 to form rectangle B, what's the scale factor in this one? 2, yeah. This right here, when it tells us it was multiplied by 2, that's the scale factor. There's our scale factor right there. Okay, well, what would the dimensions of rectangle B be then? 4 by 12, yeah, so, or we could say 12 by 4, it doesn't matter which direction we go in. Okay, its new dimensions would be, it would be a 4 centimeter by 12 centimeter. And all we really had to do was take 2 times 2 and get 4, right? And 6 times 2 and get 12. We doubled the dimensions. We doubled those side lengths. Okay, so by the way, a rectangle is what dimension figure? Is it 1-dimensional, 2-dimensional, or 3-dimensional? 2-dimensional. It has a length and a width. It's a 2-dimensional figure. It's flat. It doesn't take up any space, right? But it's got 2 dimensions, so it's 2-dimensional. Okay, so what is the ratio of the corresponding sides? Well, we know what ratio means now. We know what corresponding sides mean. What is ratio? A comparison of 2 numbers by division. I always hear people whisper. I'm not really sure what right, so they whisper. A comparison of 2 numbers by division, which we typically write as a fraction, yeah. Okay, corresponding sides, what's that mean? Ratio of corresponding sides. So ratio, comparison of 2 numbers by division. Corresponding sides, what's that?
On the opposite side.
On the opposite side. So we're in this one rectangle and we look at the side that's opposite and say you're corresponding to me? There's corresponding from one figure to the other. They're in the same spot, the same relative position in the figure, okay? So give me a ratio of corresponding sides using rectangle A and B. 4 over 2. And thank you for doing it the correct way, because when we set up these ratios, here's what we always want to do. When we write our ratio, we always want to do it new to old. Always. We always want to do it new to old. Here's what it is now compared to here's what it was before. New to old. So 4 to 2, or what's another ratio of corresponding sides we could set up?
12 over 6.
How about 12 over 6? Either way, we get what? 2 over 1, and 2 over 1 is the same as 2. So in reality, our ratio simplifies down to 2, and 2 is also what? Our scale factor, isn't it? Yeah, 2 is also our scale factor. So when they're actually asking us for the ratio of corresponding sides, it's kind of looking like it's going to be the scale factor. Right now, anyway. Okay, complete that table. Find the perimeter of rectangle A and find the perimeter of rectangle B. Find the perimeter of rectangle A, or the area, I mean, and the area of rectangle B. You know how. Perimeter is what? All the sides added together. You can shortcut that because lengths are the same, widths are the same within one figure, right? You ready for me? I'm going to do it. You're going to do it. Go. Get that pencil moving. I'm stuck. I don't know what I should put for a label on my area.
Centimeters squared.
Centimeters squared, why are they squared? Somebody caught to that? Yeah. Why are they squared? Okay, should we square them up here then in perimeter too?
No.
Why not? So when you have length, do they change from being centimeters? Do centimeters stay centimeters as you keep adding them together? Just like when you add x's together, they stay x's. But what happens when you multiply?
You're getting the area of the whole.
So now you're multiplying. So what if I had an x times an x? Would it stay x? Would I say I have 2x? I'd say I have x squared, wouldn't I? So when I multiply centimeters times centimeters, so that's really what's happening. 2 centimeters times 4 centimeters. 2 times 4 is, or it's 6, I'm sorry. 2 times 6 is, and centimeters times centimeters is centimeters squared, yeah. And what's the area of the other one? What is it? 48 centimeters squared. Okay. Well, now that we have our table filled out, we're set up and ready to answer the next 4 questions here. Number 4, what is the ratio of the perimeters? So they're asking us to compare them, aren't they? Ratio, compare the 2 numbers, show it by division. So what would it be? What would that ratio be? New to old. Well, let's start to how it starts.
32 over 6.
It starts out as 32 over 16, right? Ratio of the perimeters compared to each other is 32 to 16, which does become 2 over 1 because there's a 16 once in itself and twice in 32, and that can become what? 2. So what is that telling us? It ends up being the scale factor, doesn't it? Yeah, it does end up being the scale factor. So then what's that telling us? If we double the lengths, if we double the dimensions, as you call them, if we double the dimensions of the rectangle, what happens to the perimeter? It doubles also, doesn't it? It doubles also. So if we double the lengths of the dimensions, the perimeter also doubles. So in other words, if you double 2, and you double 2 again, because there's 2 sides there too, and then you double 2 again, or 6 again, I'm sorry, 6, and then you double 6 again, you've just doubled everything, and in reality, you could shortcut that and say, I could just multiply by, take the perimeter and multiply by 2, couldn't I? Because you multiplied by 2 every time, so you could, or you add this, and you added it 4 times, so you could just say, well, I could just double it. Okay, well then, how does the ratio of the perimeters relate to the ratio of the corresponding sides? On both. How do they relate? How do they compare? Yeah, they're both the same, aren't they? It is the same. The ratio of perimeters you know what I would like to do with this right here? I would like to, that's like a long thing to write out. It doesn't even really make a whole lot of sense to us. Because what should happen every time we have a ratio of corresponding sides? We should get the scale factors. Let's just call it that. It is the same as the scale factor. Let's just call that ratio of corresponding sides the scale factor. Because that's what should happen. If you double, and then you put them over each other, and you divide it out, you got 2 anyway, so it's really the same as the scale factor. So the ratio of perimeters, that's my it right here, okay? It is the same as the scale factors. So what would happen then if we would have quadrupled the dimensions of rectangle A? Or with the perimeters, what would have happened to the ratio of the perimeters? It would have been 4, yeah. It would have quadrupled also, wouldn't it? The perimeters would have done the same thing. The perimeter would have gotten 4 times larger. What if we had taken this particular rectangle A and instead I said, I want the scale factor to be 1/2? What would happen to the perimeter then? Would it be the same then? Would it stay the same? In B, would B's perimeter be the same as A's if we apply a scale factor of 1/2? How would the perimeter compare now? It'd be half as much as what it was in A. So the ratio of the perimeters is the same as the scale factor. Well, let's set up the ratio of the areas. What would that look like? Comparing 48 over 12, which is the same as 4 over 1, because there's 4 12s and 48, which is really the same as 4. We get the scale factor this time. Well, then what are we going to say for this one? It says, how is the ratio of the areas related to the ratio of the corresponding sides? What's the ratio of the corresponding sides again?
Scale factor.
And the scale factor is? And this was
4.
4. So how does 4 compare to 2?
Double.
It doubled. Or in other words, the scale factor was 2, and if you double 2, it's really like taking 2 times its self. Isn't 2 times 2 4? Yeah. Okay, so we could say the ratio of the areas, instead of saying it is the scale factor this time, because that's what we're going to call the ratio of corresponding sides, instead of saying it is the scale factor, we're going to say it is the scale factor. We got to be careful. We're not going to say times 2. We're going to say squared times itself. Squared. 2 times 2 is 4. 2 squared is 4. So that's how we're going to say it. It is the scale factor squared. So what is that for really saying then? What happened to the area? Compare A's area to B's area.
Double.
It doubled?
Got square.
It got squared, which is, in this case, did it quadruple? So if you double the dimensions, you're telling me that 4 of this rectangle should now fit on that one?
Yes.
Okay. You're right. Not just 2 of them, but 4 of them. Because why? We ended up doubling the sides. So really remember over here, this is 2 times 2. Over here, this is really 2 times 6. So instead of 2 times 6 for the area, we also have a 2 times 2. So we got the area 4 times bigger. So it got, the perimeter got twice as long, because that's what it does to perimeter. To area, it got the scale factor squared. Okay, now let's see what happens with the volume. Now we have to talk a 3-dimensional figure, right? To talk volume. Can we talk volume with a 2-dimensional? No, it's flat. It doesn't take up any space. Okay, it's just 2-dimensional. So we have this rectangular prism A that got every dimension it said is doubled to form rectangular prism B. So go ahead, put the new dimensions on prism B. What are its new dimensions? What are the dimensions called in a rectangular prism? What are they called? Radius? Circumference? I'm just throwing some geometric terms out here. Perimeter. What are the dimensions called in a rectangular prism? You really don't know? Length times width and height. Those are what the dimensions are called in a rectangular prism. We have a length, we have a width, and we have a height. So we're writing a new, you could call this length or width, it doesn't matter. And the other one would be the other. If you call this one the length, you'd call that one the width. And then we have our height, which doubles to 6. So we have a 10-inch. By the way, this is one place we do get to use the multiplication x to show by, the word by. 10 inches by 12 inches by 6 inches. There's its new dimensions. Okay, so what's the ratio of corresponding sides? We actually have 3 ratios we can set up here, because we have 3 dimensions. So what's one of them? 10 over 5, new over old. Not because we like the bigger one on top, it's because that's new over old. Or, what's another one? 4 over 6? 12 over 6. I thought I heard 4. I was like, where'd that come from? Okay. And then what's our final ratio of corresponding sides? 6 over 3. Well, no matter which one you get, when you simplify all 3 of those down, what do you get? 2. Hopefully we don't get a half because our prism got bigger, right? Should our scale factor be bigger than 1?
Yeah. Yes.
Yes, it should be, shouldn't it? So, look at there, the ratio of corresponding sides became our scale factor, right? Isn't the doubling the scale factor? Let's put that over here. Scale factor is 2, just in case we, wonder later. The scale factor in this one is 2. The ratio of corresponding sides came out to 2. So, what is the volume of prism A? Length times width times height. What is it?
90 inches cubed.
Okay, so it's 5 times 6 times 3, and you're telling me that's 90. 30 times 3, and it's inches what?
Cubed.
Cubed, because you took inches times inches times inches. It has to be cubed. The volume of prism B is 10 by 12 by 6, which is 720 inches cubed. Okay, so what's the ratio of our volume? What would it look like to start with? What's that going to look like? Ratio of volume, new to old. 720 over 90. What's that divide out to? 8. 8 over 1, actually, and that becomes 8. Yeah. So what's that 8 telling us?
That scale factor.
The scale factor cube. You guys think that's possible? I don't know if there's the scale factor cube. I heard never mind, I don't know what that one meant, so we have the never mind and the scale factor cube. Anybody else have an idea, Rachel?
Its volume is 8 times what the
Okay, so that 8 does tell us that 8 of these right here would fit in that. 8 of those it would take to pack that box up. So we've got the volume got 8 times bigger. So Corey says, then when we want to answer that next question, how is the ratio of volumes, which you got 8, related to the ratio of corresponding sides, which is what again? The scale factor, which in this case is 2. What relationship does 2 have to 8? Can we agree with Corey that it's the scale factor cubed is 2 to the third power? 2 times 2 times 2, is that 8?
Yeah.
It's not 6, is it? 2 times 2 is? And 4 times 2 is? 8. So we can say it, ratio of the volumes, it is the scale factor cubed. So you have to take the scale factor times itself. There's 3 factors of it. So, how many, this is a, my cube with the, I can live with this lid in case I want to start packing some little cubes in it. This is a, what are its dimensions, Austin? 3 by 3 by 3, a 3 by 3 by 3, do you agree? It's a 3 by 3 by 3, okay? So anybody want to predict how many of these little guys right here, which are cubes that are, what's this one's dimension? 1 by 1 by 1. Anybody want to predict how many of these it will take to fill up this one, Parker?
27.
27. Why 27?
Just take 3 times 3 times 3.
Okay. Why do I have to take 3 times 3 times 3?
So they find the volume.
So the volume of this would be 27, and you're saying the volume of this then must be 1. Is the volume of this one 1?
Yes.
1 times 1 times 1. Okay. So he's predicting that 27 of these should fit in here. Okay. According to what we just learned, let's do it without actually having to put 27 in here and see if it works. What was the scale factor to get from this one's dimensions of 1 by 1 by 1 to get to 3 by 3 by 3? The scale factor was 3, was it not? So what did we say should happen to the ratio of volumes? It should be the scale factor cubed. Is 3 times 3 times 3, 27. Yeah, so 3 to the third power is 27, so it should take 27 of these little cubes to fill up the bigger one, okay? How about, let's go back to area a little bit. This looks like about the size of, maybe it might be a little bit larger, but about the size of a personal pizza at Valley City. Pizza corner? Okay. So it has an 8-inch diameter, which means what? This truly is an 8-inch diameter yellow pizza. Parker?
It's 8 inches across the middle.
Okay, it's 8 inches across the center, from side to side. Okay, if I'm going to apply a scale factor of 2 to this, what will its new diameter be? 16. Okay. So if it has a 16-inch diameter, how many times larger will this pizza get? Twice as large? Okay. So twice as large because we doubled the diameter, so the pizza should get twice as large. 4 times as large. Why 4 times as large, Blake? Because it's squared. What's squared? What's it?
Ratio of
What's perimeter on this? No, there is a perimeter. We just don't call it perimeter. We call it something else. Circumference. We call it circumference. So the circumference on this, do we know it right now? No. We'd be able to find it though, right? We could take pi times 8 and we would get the, so it's about 25, let's say. Okay, so if it's about 25 inches, the circumference, that's like the perimeter. Now we'll kind of revert then to, with the pizza that has a 16-inch diameter, what would its perimeter be about? 50, it would double, okay? So, because we decided that when you double something, the perimeter also doubles. What did we decide about area? If you double the dimensions, what happens to the area? And that's what we're talking about when we say, how many times bigger would this pizza get? It's the scale factor squared. It should get 4 times bigger, shouldn't it? Let me show you that it does. This truly is a 16-inch diameter. This one's a white pizza. This is yellow pizza. This one's white pizza. This is a 16-inch pizza. How many times bigger do you think it really does? Yeah, it's more like 4. Even though we can't exactly put 4 circles on here, we'd have to cut some of the edges off and fill in the corners. It gets 4 times bigger, not just twice as big, does it? Okay? So even though it's tempting to think, but yet we're only talking about one dimension here. We're talking about a diameter. So how can that be? We're not taking something a dimension times a dimension. Or are we? How do you find area of a circle? Pi r squared. Is diameter r?
No.
How do we get the diameter or the r of this? Divided by 2. So what is the radius of this? 4. So we'd really be taking 4 times 4 times pi to get the area, would we not? And in this one, we'd be taking what times itself times pi to get the
16.
no,
8.
8. That was 16 is 8. We'd be taking 8 times 8, which 8 is 4 double. So we're really taking 2 times, so it's going to be 4 times bigger. We have to, sometimes we just have to have a visual of what's actually going to see it happening so that you can make sense to it. Okay, let's go to the back side now where we have no visual whatsoever. Number 14, we have this rectangle. It has a width of 3 inches and a length of 12 inches. Every dimension of the rectangle is multiplied by 1/3 to form a similar rectangle. The scale factor is 1/3, so it's below 1, isn't it? And above 0. It's in that 0 to 1 range, isn't it? So should our new figure be smaller or bigger?
Smaller.
Better be smaller. Okay, so we better be able to visualize that we're going to go from a bigger rectangle to a smaller rectangle, right? That's what should happen. Okay, well then it says, how would the ratio of the perimeters compare to the ratio of the corresponding sides? What do you think? How would they compare? Remember, ratio of corresponding sides really means what?
Scale factor.
Scale factor. Let's just write that. Scale factor. So how would the ratio of the perimeters, so this one's perimeter, the new one, compared to the perimeter of the old one, how would it compare? It's going to be 1/3, isn't it? The new, what new one's perimeter is going to be 1/3 the perimeter of the old one. Because remember, what did we say? The ratio of the perimeters is the same as the scale factor. So we could say it is the same. 1/3. It's gonna be 1/3. The ratio of the perimeter is gonna be 1/3. We do not even have to find those perimeters, but if we did, and we put the new perimeter over the old, it would simplify to 1/3. So you can, on your own time, you can test it out and see if it works, okay? How would the ratio of the areas for this same group of rectangles, how would the ratio of the areas compare to the ratio of the corresponding sides? How would that comparison turn out?
It would be 1/6.
1/6? No. Then what would it be?
1/9.
1/9. Oh, now you get Corey's bobblehead going.
It's the scale factors.
It's the scale factor squared. Oh, area, two-dimensional, squaring, something times itself is squaring, two-dimensional. So how would the area, it is the scale factor squared. Remember, ratio of corresponding sides is the scale factor. So it would be 1/3 times 1/3, which would be 1/9, not 1/6, right? 3 times 3 is 9. So the new rectangle would be 1/9 the area of that one's rectangle. 9 of these should fit on that one. Anybody have any questions on that one before we try another one? Okay, well then, next one we have a triangle involved. With this triangle, they tell us what its area is. It's 20 inches squared. Every dimension of the triangle is multiplied by a scale factor of, oh, do they tell us what the scale factor is?
3.
Do they tell us what the scale factor is? Or did you find it? Does it tell us here anywhere?
No,
Okay, so where'd you get 3?
I was looking at the wrong.
Oh, okay, so we're on this one, right? Okay, so every dimension of the triangle is multiplied by a scale factor, and the new triangle has that area. What was the scale factor? We don't know it, do we? That was our question. So how are we going to find it? Are we going to start drawing some triangles and see if we can get some triangles that have those areas, or what are we going to do? Maddie? 100 what? And divided by what? Okay. So what would this really be called when we put 180 over 20? What are we setting up? What is that? Ratio of what?
Area.
Yeah, ratio of areas. That's what we are finding here, aren't we? Well, can that be simplified? 180 over 20. Anybody know what that simplifies down to? 9 over 1, which becomes 9. Okay. So we now know the ratio of areas. Was that the question?
No,
What's the question?
what the scale factor?
Oh, how are we going to find that now?
Divide 9 by 2.
Divide 9 by 2, so the scale factor is
Oh, wait, no.
4.5?
Kinda square root.
What? Remember, the ratio of the areas is the what of the scale factor?
The scale factor square.
It's the scale factor squared. So the ratio of the areas is the scale factor squared. In other words, something times itself, right? What number times itself is 9? 3. So our scale factor, let's circle one of those 3's. Here's our scale factor right here. The dimensions were tripled. Now, let's make sense of it. Does it make sense that the scale factor could be 3? 3 is greater than 1, which means then our new figure should be bigger. Is it bigger? Yeah, went from 20 inches squared to 180 inches squared. That's bigger, right? It got bigger, so our scale factor should be greater than 1. At least we got that. We can feel kind of good about that part of it. But if we would have gotten 4.5, we would have had the wrong answer, wouldn't we have? Okay, now we got a cylinder. Oh, now we're moving to 3-dimensional, right? Has a radius of 3 centimeters. That means, you know, like there's a cylinder, I'm going to have it laying on its side here. It's got a radius of 3 centimeters, and then the length, or kind of like the if I stood it up, it'd be the height of it, is 10 centimeters. Every dimension of the cylinder is multiplied by 3 to form a new cylinder. So will the new cylinder be bigger or smaller? Bigger. How would the ratio of the volumes compare to the ratio of the corresponding dimension? Ratio of the volumes compared to the ratio of the corresponding dimensions. Did they give us the volume this time?
No.
Okay, got any geniuses in here who know how to find the volume of the cylinder? This is your chance. Okay, Blake.
Area of the circle on the top times the height.
Okay, so you gotta find the area of the circle, which could we do that, by the way, if we know its radius?
Yep.
Yeah, we could do it, and we know its height, because that's really the same as the length, isn't it? If it's laying on its side, it's called length, if it's laying like this, it's called its height. So, could we find the volume of the cylinder? But that's a whole lot of work. I don't wanna do it. IR squared H, that's how we find the volume of the cylinder. Do you really wanna work that hard? Okay, then let's find another way. How would the ratio of the volumes compare to the ratio of the corresponding dimensions? What's that called again?
Scale factor.
Scale factor. Okay, that's a scale factor. So basically they're asking us, what's going to happen to the volume? Is it going to get, we already decided it's going to get bigger, right? So how many times bigger is it going to get? 3 times bigger? So the cylinder, the old cylinder, 3 of them would fit in the new cylinder and fill it all up? 6? 9? Just throwing out numbers like crazy here. I wonder which of them were right.
Because it'll be a scale factor.
Oh, but let's go to the front. What did it say? The ratio of the volumes is the same as this. It's 27. Why?
27.
Why?
It's the scale factor cube.
It's the scale factor cubed. When we're talking about volume, 3-dimensional, now we have to take the scale factor times itself. We have to have 3 of them. 3 times. We have to have it cubed. So what we're going to have to do is we're going to say, if it was multiplied by 3, we have to say, what is 3 times itself, 3 cubed, what does it equal? And Corey said 27. You agree with him? So the ratio of the volumes becomes, so our ratio of volumes, it is 27 times bigger. Not 3, not 6, not 9, 27 of them. It's just like that cube I was just showing you guys, right? 27 of them fit in here because we tripled the dimensions. Okay? Okay, and number 17. 3-dimensional or 2-dimensional or 3-dimensional? A cone has a volume of 36 pi centimeters cubed, and every dimension is multiplied by a scale factor. What is it? Oh, to form a new cone. The new cone has a volume of 288 pi. What was the scale factor?
288.
So can we set up a ratio of volumes? Can we do that? Because they gave us that, right? So we could say new to old. This is where you're going to get thrown off. You're going to want sometimes just to put it in whatever way looks convenient for you. Always say to yourself, new to old. So 288 pi over, or don't change that to 3.14. You're going to see we don't need to. 36 times pi, 36 pi. What's that simplified to? 8? You guys agree with Dawson? He says 8. So in other words, the pi's can cancel away, right? And then apparently he thinks 8, 36 is going 288. Well, what's 36 double? 72. Can you just look at 288 and tell me how many 72s you think we should be able to take out of 288? 7, 28. So what do you think? Do you think this is, we doubled it? So 4 times 2 is 8. I think Austin's right. It does divide out 8 times. You can take 36 out of 288 8 times. So the ratio of the volumes is, is 8. I don't really want an equal sign there. I just wanted to say the ratio of the volumes is 8. They want the scale factor. So is that our answer? No, they weren't asking for ratio of volumes. They're asking for the scale factor. How do we get the scale factor from the ratio of volumes? Something times something times something equals 8. What is that? Something. 2. So the scale factor is 2. The dimensions of that cone, oh, not scale dimension, scale factor. The dimensions of that cone were doubled, weren't they? And it made the cone get 8 times bigger by doubling the dimensions of it. Okay. Now, we don't have time to do these last two, and we didn't this morning in class either. Yes, Josh?
What would be your labels for 27 and 8?
They don't need labels because they are a ratio. They're not a rate, they're just a ratio. That's pretty simplified. I expect you to do 18 and 19 on your own in these notes, okay? We will talk about it at the beginning of class tomorrow. Make sure you carefully write down the problems you have to